Hello everybody, welcome to this presentation where we'll look at the analysis and FEA of composite structures using MSC Apex. So we'll be focusing on a number of topics, looking at model build, analysis and optimization. So first of all, we're going to take a run through in terms of model build, looking at a typical structure. So we've got an example here focused on a bike frame. Pretty interesting given that a bike frame has some fairly complex loading and composite structural definition. We're going to take you through the process or look at the FEA model build from the underlying CAD definition, and then focus on the structural properties, so looking at composite materials, plies and zones that make up the overall composite structure. Then we'll move on to analysis. So we'll look at some specific loading, and in this case, of course, focused on the bike frame. So we'll look at various load types such as the pedaling action, the load through the forks and load through the seat due to standard riding conditions. And we'll use these load cases to understand the strength, stiffness and stability of the structure for a baseline composite design. Then we'll move on to structural optimization, again using MSC Apex and focusing on the Nastran workflow for the specific optimization approach. So here we'll look at algorithms to determine the optimal laminate construction, so very complex set of zone and laminate ply definitions for a bike frame, and we'll be looking at these optimization algorithms focusing on minimum mass whilst respecting stiffness, strength and stability constraints. Okay, so once we've got our optimization process up and running and the ability to predict the optimal structural configurations, we can then look at how we might change some of the inputs to our analysis models and optimization models using a parametric approach, whereby we can update things like loading and material types to show the influence of the optimization on updated structural properties and performance. So we'll get started with the steps involved with model build using MSC Apex. So we're going to look at the CAD to mesh approach. So there are many tools in Apex to allow a very efficient FEA model build, looking at direct modeling, which gives us very good geometry control, surface and mesh manipulation, and then the quality checks required to give us a good quality mesh definition for the downstream FEA analysis. We'll look at the definition of, or rather the generation of composite materials, looking specifically at plies and zones, and we can focus on orthotropic materials pertinent to typical UD and woven cloth type materials, zone definition, plies, and we've got the capabilities as well to look at orientation for fibers in different areas where draping and that kind of thing might be apparent. We've got a number of utilities in the Apex environment that allow us to import materials, sheets and plies and stacks and laminates to update or to build and update our composite models very quickly and easily. And then of course we've got our loading and boundary condition definition. So we might want to look at specifics for this particular type of composite structure. So I mentioned already the pedaling action, the fork action and the seat loading action that would be pertinent to this kind of approach. So we'll get started looking at a demonstration in the Apex environment. Okay, so here we are in the MSC Apex environment. We've got a CAD model in 3D space for a lightweight road bike, so typical of a composite construction, so obviously a good example for the kind of thing that we're looking at. we've got componentry shown in the model. That's going to become useful for defining our loads and boundary conditions. So even though we're only concerned with the frame analysis, it's useful to have that kind of structure in there as well. So if we look at the model that's been built, we got various parts and assemblies that represent the full structure. So here we've got a surface definition that's been built from the underlying CAD model, and we can show the FEA-based mesh that's in that's been applied to that surface geometry. So lots of features that make up the original composite construction for the head tube, the bottom brackets, so showing the tube interfaces where they come in at these critical regions. We can look at element quality. So this is a measure of how well the mesh has been defined on the structure. So generally speaking, massively dominated by green, good quality elements. We've got some areas where the quality isn't ideal or isn't perfect, especially where we've got lots of curvature, but will be good enough for the type of structure that we're looking at here. We've got solid mesh regions for some of the thicker regions, so the rear dropouts, a typical example there. We've got the fork idealized based on a sort of standard certification type loading, so maybe the ISO loading constraint. So we've got a rigid bar that represents the fork, and we've got some joint definitions that can be used to model or to idealize the bearing interfaces, so allowing moment transfer or the appropriate moment transfer at the head tube and at the bottom bracket interfaces as well. Okay, we can use a colored, well, we've colored the regions in a manner to allow us to help with our zone definition, and we've got something called a mesh independent tie, a mesh dependent tie between these discrete regions to allow us to connect the model together but still respect the discrete composite zones within the model. So if we look at the head tube as an explicit zone, we can start to understand how the materials are referenced to build up those composite properties. So we've got a UD fabric system set, so we've got things like the stiffness and strength, or the modulus and allowable strengths defined in there, and we can show those for a woven fabric as well. So we're specifying our material definition. Once we've got those material behaviors set, we can start to build up our laminate stacking sequence for a typical build. And then we've got those set, we can then apply those laminate behaviors, or that laminate stacking sequence, to the zone of interest. So we can double click on the zone in the model browser on the left hand side, look at the orientation of a given zone definition, and we can have multiple coordinate frames that specify different directions for a given region. If we may have a complex draping action, we might want to look at local definitions. And then for our discrete plies, we've got our application region and our orientations shown on screen here. And we can flick through different plies within the stack and see how those orientations are set. So we might have a woven cloth at 45 degrees and then a UD material at 0 degrees, relevant to the particular build sequence for the structure. Okay, so we'd repeat that for all of the zone definitions, and then we can show a map of the thickness plot. So we've got a uniform laminate here to start off with, and we can see our thickness going inside the outer surface, as it were, and again reflective of our build sequence within the structure. We can do what we call core sampling, so we can cycle our way around the structure and look at our ply definition and the coverage for discrete regions. Okay, many different ways of creating this stuff. So we've shown the manual approach, but we can use the embedded Python API within the Apex environment to read in discrete materials and stacking sequences from external sources. So we can read in Excel data discretely to build up our zone definitions. Okay, so just showing quickly here. So we can bring in the sheets, which are the ply materials, so material and thickness, and then our stacks, which are our stacking sequences. Okay, so once we've got our model built, or our structure built in terms of the geometry, the mesh, and the properties for the composite structure, we can then start to build up our loading environment. Okay, so we were looking at 4 discrete loading cases here. So pedaling action on the right and the left hand side, and a load through the fork and a load through the seat. So by having the external geometry visible, we can see the influence of those loading actions. So here we've got the fork fixed, a load applied through the right hand pedal, and then a constraint where the rear wheel meets the ground. And this is typical again of a standard ISO type loading environment. Okay, we can show the application on the left hand pedal. Okay, and again this is reflective of the ISO condition, and then cycle our way through for the fork load. So this is a load applied in a horizontal sense at the fork, and the rear axle is pinned. Okay, and we do the same again for the seat loading. And again, Apex is really useful in terms of being able to control both the loading action, the constraint action, and any rigid members which might be used to apply those loads into the structure. Okay, so again we can see that for the seat loading action in there. Once we've built the FEA model and we've got the mesh developed and the composite properties set as we want, then we can look at setting up our load cases, and this would typically be done for loading and constraints. So we need to specify how the model is going to be loaded and how the model is going to be constrained or interact with the rest of the structure. Okay, we can then look at our results. So generally speaking, for composite structures, we'll be interested in the strength, maybe looking at the ply and laminate failure indices, the displacement of the structure to give us an idea of the stiffness, and then potentially for a composite structure, which generally speaking will be a thin wall construction, stability or buckling is often very important to consider. We've also got the ability within Apex to do what we call generative model update. So this allows us to modify areas of the geometry and or the mesh, and the model will be updated automatically, so we don't need to redefine our loading and our properties and our mesh definition to understand the impact of these changes. So we'll take a look at this through a quick example in the Apex environment. So once we've got our loading and boundary conditions set up, we can develop our analysis by specifying the output requests and the events that we're going to look at. So we've got 4 events or 4 load cases here: pedaling action left and right, the fork action, and the seat loading action. So in this table here, we just specify which loads and constraint sets are applicable to a given analysis. Okay, we've got the ability to look at different load types as well. We'll look at stability in a moment, but first of all we're going to solve this for static analysis. So run through the embedded Nastran based solver within the Apex environment, and then this will give us output which we can assess for the 4 different load types that we've got. So just showing the displacement output here. So we've got the right hand pedaling action on the top left, we've got the left hand pedaling action top right, we've got the fork loading action shown in the bottom left, So just animating this. So the fringe plot is showing displacement, and then the same for the seat loading action shown bottom right. Okay, so neat aspect of Apex is that the loads and constraints which are pertinent to a given solved event are shown on screen at all times, so you can see exactly what loading is being used to induce the response. So looking at the pedal, the right hand pedaling action here, we can look specifically at some of the output, and we're looking at failure indices here. So we can look at, this is the SIWO failure index. So this is a measure of the sort of combined load states for a complex composite region. So looking at the head tube and the bottom bracket, just showing the mesh in there, and we can see that the type of response and cycle our way through the structure. We've got the ability to look at these strength outputs on discrete regions within the model. So given our zone definition, so this might be reflective of the build sequence for the composite structure, and we can look at which type of plies and materials and how they're loaded and how they'll influence the overall structure. Obviously lots of information here, so pretty complex to assess or to update from an optimization perspective, which we'll come on to in a moment. But we can see the discrete behavior of each one of these output quantities for our given ply stacking sequence and laminate. Okay. Lots of information that Apex gives us. We can run different load types as mentioned. So this is a stability case, so a buckling case. So we can look at the displacement and the load factors that are developed for this kind of analysis, and see here a table of values that's generated. And we can see here the peak displacement is at the interface between the sort of thinner section of the top tube where it meets the stiffer seat mount or seat junction. Okay. Generative update is something that's pretty important within the Apex environment. So we can look at one particular zone and look at the thickness distribution and definition here. And we're just going to show you how we might want to manipulate the model. So we've just got a couple of dummy surfaces here, and we're going to split the underlying structural mesh or the structural zone definition using these surfaces. And that will give us the new splits in the mesh definition, and then we can look at things like remeshing or changing some of the design features. A pretty simple example here, looking at remeshing for some of the detailed features. So we can see we've cut these faces out of the original zone definition, remesh based on a tighter element edge length, and then specify the faces in the model that we want to remesh. Okay, so we might be interested in a design change or some increased level of fidelity for this particular region. Many reasons why you might want to change the model, but all of those changes are updated automatically given Apex's generative update capabilities. And we can look at the zone definition and the thicknesses and ply distributions have been maintained even though we've changed the mesh significantly. We can look at the influence of those changes in the Apex environment, and we can store multiple sets of results to allow us to compare two different types of models in a single environment. So with our model built and analysed, we can now start to look at the optimization of a structure. So obviously there's very many parameters in the composite build, and it can be very difficult to try and optimize these. So generally speaking, traditional composite optimization may be using classical sizing methods, which generally speaking would look at the load transfer, the load distribution in a structure, and then try and understand what laminate and ply definitions are required. Can be very laborious and involve many iterations to come to a working structure. And generally speaking, this won't give you an optimal approach, certainly respecting things like light weighting and strength and stiffness and stability through our load application. So with this workflow that we're looking at, we're focused on an FEA-based optimization, whereby we can look at detailed ply definitions. So there are many different optimization techniques from an FEA perspective, looking at things like generative design and topology optimization, where we're looking at an overall shape distribution. Things like topometry, which look at different thickness maps over a given structure, and then sizing algorithms, which are used to look at specific properties in the model. So in this example, we're going to be focused on ply-based sizing, which allows us to look at things like material selection for our ply generation, or applied materials, maybe UD definition and woven cloth definitions, our orientation, so how the fibers are oriented over a given structure, and then the thickness and the number of plies that we might want to specify within the region. Okay, so to perform an optimization analysis in its true sense, we need to define our problem pretty carefully. So generally speaking, for this kind of structure, again, we're going to be looking at things like minimizing the mass, minimizing the amount of material that's being used, which ultimately could be used to influence a sort of minimal production cost approach. And we want to maximize our structural performance again. So we've got, again, many different approaches looking at strength, stiffness, and stability. The way that this works from an optimization perspective is that all of the parameters in the model are updated simultaneously in an iterative manner to give us our objectives and ensure that our constraints are met. In this particular example, we're going to look at how Apex will interact with MSC Nastran from an optimization perspective. So we've got the ability to export a Nastran deck from the Apex environment. We're going to be looking at a SOL200, which is the sizing-based algorithm within MSC Nastran, and we're just going to take a quick look at a web tool developed by a third-party distributor engineering lab. Pretty interesting way of developing SOL200 type data. And then we'll be looking at the optimization tools and how we might then want to update our models and look at our results based on the optimal configurations. So we'll take a quick look at the Apex workflow for composite optimization, and specifically focusing on an export to the Nastran environment for the optimization procedures to take place. So once we've run our baseline model and we're happy with the response, we can export the Nastran data. I'm just showing here the Nastran definition as exported. So Apex has exported a SOL101, so a linear static analysis. And in that definition, we've got our 4 events or 4 subcases set up for the 2 pedaling actions, the fork and the seat loading action. Okay, I'm going to show you a tool developed by the engineering lab here, which is an external web-based application which allows you to input standard Nastran model definitions and convert them into a SOL200 type optimization definition. So pretty useful here from an Apex perspective, that we can develop our Apex model and then set up all of our optimization information based on these parameters. So just running through a couple of procedures here to specify the model parameters that we want to change. So we might look at ply thickness, but we can equally look at ply orientation, material definition, and what have you. Our objectives, which is a minimum mass solution. Our constraints, which could be composite failure or composite strengths or stiffnesses. So many different types of constraint that we can set up in our models. Okay, so we can see that the Nastran data has generated. We can relate those to specific subcases. So we've got 4 subcases here with all with the same constraint set, but we can play tunes with this if required. and then we can export the Nastran optimization data for external solution. So here we've got some of the data that's developed. So this is based on our baseline Nastran exported data, but has been updated to consider our optimization criteria. So we can see we've got what we call an include file, which references all of our design variables. So these are set up in this example as our ply thicknesses. We've got our range for discrete ply optimization or ply thickness optimization. We've got our responses, so mass, which we're trying to minimize, and then our constraint, which in this case is a composite strength, so a control on our failure indices that are calculated by Nastran. We can run the solution, and this is some of the text-based output. So don't get too scared by this if you're not used to Nastran, but effectively we're showing here that we've got an iterative solution that's run through. So the optimizer is updating the parameters to try and achieve our objective for our constraint set. So the solution is solved here after 6 iterations. Our objective is minimum mass. So we can see that the mass is reduced as we run through the solution. We can see our constraints are satisfied. And then our parameters, in this case, are our ply thicknesses. So we can see how they've changed through the optimization sequence to give us our solution. The optimizer has predicted a series of ply thicknesses, which are developed for our discrete zones within the composite model. And then we can run through some automation that we've got set up, just shown here in a tabular sense, but this is all run using some Python and Excel data in the background, which interacts nicely with our Apex model definition. So we can see that on the bottom we've got our stacking sequence against each zone within the model that's developed, again, for a minimum mass solution and respecting our strength and stiffness requirements in the Apex environment. So just looking at the model that's been developed and updated with our new laminate sequence, so we can see our thicknesses, how they vary across the model based on the optimization output. And then we can look at our zone definition for a given region. So here focusing on the head tube, and we can look at the laminate stack that the optimizer has predicted, and then run through the discrete ply definition and thicknesses that has come out of the optimizer. Okay, so really powerful techniques here to allow us to predict our optimal structure based on the huge parameter set that we've got. And bear in mind, this is a relatively straightforward bike frame model with a fairly limited subset of zones, but again, we've got we've used the optimizer to define our thicknesses for this region. So we can see here the 3D thickness that's developed for the piece of structure we're looking at. If we were to look at a section view, again with our thicknesses shown, so the head tube and the seat junction are doing a lot of the work for these load cases. We've hidden some of the internal structure here, specifically at the seat tube interface, but we can see here the change in thickness. So we can bring in lots of Apex advantages here to maybe develop our drake ply definitions and also our ply drop-offs, and then ultimately we can look at our structural response. So we've got much reduced weights for better structural behavior. So with the optimization model set up and working, we can now look at things or changes to that optimization model, which are involved using a parametric model update. And this approach can predict a new optimized model based on changes to model and or loading. So for this type of structure, a couple of things that we might want to look at might be an influence to or a change to the applied load levels. So maybe a rider might have a different power output or different weight characteristics, and therefore change to the structure. And also things like changes to material definition as well. So theoretically, we've got the ability to define an optimal structure given specific rider inputs and specific material systems. So running this kind of approach, so we won't go through all the mouse clicks and what have you involved, but we've looked at a typical frame structure for two different material systems, and we've looked at we've got shown on the table here the influence of two different material systems. So we can look at the parametric update, and by running through this, we've been able to demonstrate a 20% mass saving by going to a second material system using the same objective, so a minimum mass, but respecting two different constraint systems. So with these updates run through, we can look at the zone table and ultimately the composite structure between the two different concepts. So if we focus on two different regions, so maybe the head tube, with material system 1, we've got a stacking sequence. Material system 2, we might predict a different stacking sequence and a different use of material within that region. For the seat mass junction region, lots of load distribution of the load transfer going on here. So we've got a different laminate predicted for two different materials systems where we might have different strength and stiffness characteristics. So to summarize, we've looked at a number of different tools and techniques within the Apex environment. So we've got the ability to develop a high fidelity composite structure. So we focused on the ease of CAD to mesh, model QA, looking at mesh quality, and we saw that some of the detailed composite zone and ply definitions as well. We've assessed the baseline concept under a range of different loading conditions, the pedaling action, the fork action and the seat action, and understood things like the strength, stiffness and stability of a structure. We've then moved on to looking at optimization techniques, which allow us to predict optimal build parameters, and again focus specifically on composite zone and ply stacking for this type of structure. And we've also got the means of looking at parametric updates to predict the optimal structure under different conditions. So very easy to update the optimization model to see the influence of loading and material changes. We've also got productivity tools in the Apex environment, again generally focused on the Python API, which allow us to update the baseline model with our optimal configurations very quickly and easily. These techniques that we've looked at, whilst in this particular example are focused on composite structures, they can be used to define optimal structural configurations for different construction methods, maybe looking at metallic structures or additively manufactured structures, or hybrid approaches where we might look at AM with composite structure in the same type of design. So if you want to learn more about Apex and some of the techniques we've talked about here, visit evotechcae.com, learn Apex, and there's lots more capabilities in there through our subscription-based courses.